Hello everyone, meet Ashraf. Yep, that's me. I'm going to share with you about a mini review on quantum entanglement, a core resource in quantum computing. You might wonder, what is quantum entanglement and quantum computing? Why quantum entanglement is so important in quantum computing? In this video, I will answer all the questions. Before I start, here are the contents of the presentation. The first part will be introduction, followed by methodology, quantum entanglement, and quantum computing. Now, let's jump right into the first part. In 1935, three people had a thought experiment discussing on their finding of a fascinating phenomenon called EPR paradox, named after Einstein, Podolsky, and Rosen. Later, a physicist named Schrödinger addressed the concept discussed by the three gentlemen, refers the phenomenon as an entanglement phenomenon, and he also did not truly understand why it violates the theory of relativity. Few decades later, a physicist named Bell showed that quantum entanglement violates the principle of the theory of relativity. Quantum entanglement is a core feature in quantum mechanics. It is a very bizarre phenomenon. How to describe it? Well, when two or more objects are entangled, it's called quantum entanglement. The state of one object can automatically provide the information of the state of the other object, regardless the distance between them. We will investigate this better very soon. Quantum entanglement has become the foundation for quantum information processing and use in various fields such as quantum computing and quantum cryptography. Quantum entanglement is the key ingredient for quantum computers to demonstrate the power in computing capabilities over classical computers. Over the years, interest in quantum entanglement has grown and significant progress has been achieved in quantum computing. For example, in 2021, IBM has revealed its latest quantum computing chip named Eagle packs in 127 qubits. What is a qubit, you may ask? We will investigate this very soon. The second part is the methodology. In this research, we use literatures from the year 1935 until 2021. Here is the flow of the methodology. First, we search for literatures with specific keywords: quantum entanglement, quantum computing, and quantum state in citation index journal and other forms of publications. Then, we perform deductive method for information analysis and then literature selection and document analysis. Now, let's get back to quantum entanglement, shall we? As mentioned before, when two or more objects are entangled, it's called quantum entanglement, and the state of one object can automatically provide the information of the state of the other object, regardless the distance between them. In simple words, here is an example. There are two coins. One coin has head as a value and the other one has tail as a value for both sides of the coins. A coin each are given to two people, Alice and Bob. Both people are separated far away. Alice is on Earth and Bob is on Mars. They were told that the coin that they currently possess must be either head or tail. In this situation, their coins are correlated, entangled in a classical way. Assume that both Alice and Bob are at their destination. Alice looks at the coin, found out that she has the head. Once Alice knew the value of the coin she has, simultaneously she knew Bob's coin. There you go. Now you know about the concept of quantum entanglement. Now, let's get technical. In quantum mechanics, a quantum bit, or known as qubit, is the basic unit of quantum information. To put it into perspective, a classical computer which we use every day, they use bit to carry information. In quantum computer, they use qubit or quantum bit to carry information. In classical computer, a bit can carry 0 or 1 as a value, but in quantum computer, a qubit or quantum bit can carry 0 and 1 at the same time. In quantum mechanics, it is known as superposition. A superposition is defined as the ability of quantum system to be in multiple states at once. A qubit vector state unit is denoted as. Superposition can be denoted as. Blending in the principle of entanglement and superposition would be a great supplement in the computing power. Now, let's move on into the quantum state. There are two types of quantum state, pure state and mixed state. A pure state can be described by a wave function. A mixed state can only be described by a density matrix. A pure state can be described as, and a mixed state can be described as. Moving on to the last part, quantum computing. Classical computer versus quantum computer. Quantum computer was proposed to simulate processes that a classical computer cannot achieve. Quantum computer utilize the collective attributes of quantum states such as superposition, interference, and entanglement, abiding to the quantum mechanics principle rather than classical physics principle. Major difference between a classical computer and quantum computer is the pace of solving computational problems. For example, let's say both computers are given computational problem to execute. A classical computer would take a month to complete the task, but a quantum computer could take on the task in 2 minutes. That's how powerful a quantum computer is. And now, they are not planning to stop increasing the power of quantum computer. How to increase quantum computers' power, you may ask? The answer is quite simple. To increase the power of quantum computer, simply increase the amount of qubit or create a larger entangled state. Next, we are going to the applications of quantum computing. Here are some of the applications. First one, quantum computing in cloud, quantum computing in industry, and quantum computing in security. Let's go through the first one, quantum computing in cloud. Cloud-based quantum computing services have been introduced and used in several backgrounds, namely teaching, research, and game. Cloud-based quantum computing provides a quantum computer platform that can be accessed publicly by anyone in a cloud environment setting to test or execute a real quantum processing task. Here are some existing cloud-based quantum computing platforms: Microsoft Azure by Microsoft, IBM Q Experience by IBM, Quantum Playground by Google. Next, the second application of quantum computing is quantum computing in industries. In the future, quantum computing will revolutionize various industries, such as chemicals and petroleum, distribution and logistics, financial services, healthcare and life sciences, and manufacturing. For example, in healthcare and life sciences, utilizing quantum computing will help new drug discovery, accelerating diagnosis, and personalizing medicine. Lastly, the third application of quantum computing is quantum computing in security. Data security is essential in many aspects. In the modern world we live in, we rely on computer systems. Effective data security is extremely vital. Even though cybersecurity has been constantly improving, the counterpart, cyber threats, have also improved. Experts in the field use cryptography to protect the information from unauthorized access, ensuring the integrity and authentication of the data. What's the difference between classical cryptography and quantum cryptography? Classical cryptography is based on computational mathematics, and quantum cryptography is based on quantum mechanics. Let's break it down into a classical cryptography versus quantum cryptography with example. In classical cryptography, Alice wishes to communicate with Bob using an insecure channel, such as Internet. By using an agreed-upon key, Alice and Bob can make use of the crypto system and protect the information transferred, even with the insecure channel. Considering that the channel is insecure, an eavesdropper, unauthorized personnel, named Eve, may still tap into the communication channel and intercept the information using specific method to decrypt the information. In quantum cryptography, Alice wishes to communicate with Bob over an insecure channel, such as Internet. To encrypt and decrypt the information sent over the insecure channel, Alice uses a series of photons with random basis, rectilinear or diagonal basis assigned to each bit sequence, then transmitted to Bob through a quantum channel. The photon's polarization will then be measured by Bob using a random basis. Suppose that Bob measured the same polarization as Alice, then Bob received the intended bit sent. If Bob chooses the wrong basis, then the bits he read is random. Next, Bob will notify Alice the basis he used, and Alice will report back if Bob had chosen the right basis. Alice and Bob will discard the bit measured with different bases. Both Alice and Bob should now have an identical string of bits called secret key. After consistency is ensured, both now have the shared secret key. Discarding noise and measurement error factors, if the measured bit compared are different between Alice and Bob, it indicates the presence of an eavesdropper named Eve on the quantum channel, resulting in Alice to send a new generated bit sequence. To decode the photons, Eve would have no choice but to measure the photons transmitted before reaching Bob with random basis. The no-cloning theorem assures that Eve could not replicate the unknown state, thus distorting the photon sequence sent to Bob. Therefore, the photon received by Bob will be random and 25% incorrect compared to Alice, considering the error rate of 50% made by Eve. This will resulting in Alice to send a new generated bit sequence. The chance for Eve to obtain the secret key is slim to none if sufficiently long bit sequence is compared. That's how quantum cryptography makes cyber threat impossible. Conclusion: a review of quantum entanglement as a core of quantum computing were presented. The differences between classical computers and quantum computers were also discussed, focusing on the utilization of quantum entanglement in quantum computer, which is an important key in enhancing the power of quantum computers' processing speed. Next, some existing quantum computing applications were also presented. Even though quantum computing may be considered still early in the development phase, considering the current quantum computers' limitations, quantum computing has a huge potential to change the technological world. That is all. Stay safe. Thank you.